Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Vancouver. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE Control Systems Society. Our guest today is Miroslav Krstić, Professor and Senior Associate Vice Chancellor for Research at UC San Diego. Welcome to the show, Miroslav.
Thank you very much, Alberto. Thank you for inviting me and also for creating such a wonderful podcast series.
For me, obviously, it's an honor today to sit here with you for this conversation. I was completely blown away by the breadth of your work, and I hope to do justice to it in this conversation today. As you know, most of the times we do proceed chronologically, but I thought that today we could actually proceed thematically, maybe with a small digression on where did you grow up and how that affected who you became.
So I grew up in a relatively small town of 30,000 people called Pirot in former Yugoslavia, almost as far away from Belgrade as it gets. And the place, though provincial, had a very good high school, perhaps because it was so isolated, it built one. And it was a high school experience full of many, many interests and distractions. I was not any kind of a prodigy. I was spread in all sorts of directions and to numerous infatuations. Math and physics did come easily, but there was playing the guitar in a band, devouring fusion and jazz records, being seduced by philosophy in the 9th and the 10th grade, competing nationally in French language and ranking 5th. Somehow, I ended up the valedictorian in my high school graduating class, but I consider that simply as staying afloat. All of these distractions and pulls might have been an early sign that control, something universally applicable, was in my future.
Amazing. I was actually looking up the Wikipedia page that is available for your profile, and I read that you graduated from the University of Belgrade, ranking top 1% in your class. And I'm curious about what made you choose control.
So first, I chose control as an electrical engineering student, and I chose electrical engineering as a subject in which you don't have to choose between math and physics, the two most fundamental subjects. My favorite college class was in the second year, analog electronics. And control caught my attention in the first lecture, where the professor walked into the room and inverted the saying, all beginnings are difficult, into all beginnings are easy, and proceeded to sketch something that we didn't know yet what it was. It turned out to be an operational amplifier. He added two resistors to this sketch, one connecting from the output of the op-amp to the negative node, the other one from the negative node to the ground, and demonstrated to us how, in order to assign the gain of this overall amplifier with a feedback connection, it doesn't matter if the gain of the op-amp is 1,000 or 100,000, that the mere fact of closing the feedback loop with these two resistors allows to assign the gain of the overall amp with the values of these resistors, or simply with a potentiometer. Now, how cool that is to somebody who used to play the guitar, I cannot describe, but it was clear already that this concept was, in some vague way that I had not yet understood, was independent of the physics of what was happening or of the hardware realization. And then in the third year of my 5-year program in electronics, there was a class on automatic control. And through that class, I realized that there is a specialty, which if I choose, I may never have to deal with anything other than equations for the rest of my so-called engineering career. So that's what I chose. And then this program, this was a 5-year program, so it might sound surprising, but there were 7 semester-long undergraduate control courses. So I got to see linear frequency domain, state space designs, digital control, stochastic signal systems, optimal control, state estimation, some basics of nonlinear systems, and glimpses into system identification and adaptive control. That's what pulled me into control.
And they all show up in your future career, have all the keywords that you mentioned. So it's great to see how that period of your life actually propagated, if you want. So I'm curious, what made you make the move to the States, to Santa Barbara for your PhD? How did that happen?
So first of all, that was not in the plans at all. I had married my freshman math honors classmate, Angela, and we were married and right after graduation and building our lives in Belgrade. I took a job at the university, but was appointed to teach a control class to students majoring in mining engineering. And in that environment, I also started playing with research in control fluid networks of general topologies, which was a good fit for an electrical engineer. And they were motivated by mine methylation networks. These are actually PDEs, gas dynamics, Euler equations, and nonlinearities, something really, really new that I hadn't seen in circuits. And I produced results, but I had no idea where one would submit that from Belgrade, and I ended up publishing those about a decade later in Systems and Control Letters. So at that time, things started changing in former Yugoslavia. The wars that were to follow in the 90s hadn't blown up yet, but it was clear already that the future for Angela and me professionally was pretty dim. So Angela was watching me buried into these pages of equations and consumed with them, and then just softly asked, why don't you apply for a PhD in America? So I did immediately, instantly, tomorrow, started looking into that. I had no idea what that even meant. I had taken some class in which the most cited person was some Peter Kokorovich, obviously somebody who came from the university that I had finished and would be calibrated and applied to several places, including to Peter. And Peter Kokorovich was persuasive about joining him at UC Santa Barbara, where he was just moving after retiring to University of California. I decided to leave on the table an admission I had from MIT and head to Southern California with Angela to do nonlinear control.
Amazing. And that's the start of an incredible chapter of your life, at least based on the records that I see. It makes me feel excited just to talk about it. I heard at least about an anecdote. I'm wondering whether it's true. So I think in time we're settled in around 1991. And you moved to California, as you say, to start your PhD with Peter Kokotovich. And just maybe in a few weeks, you write your first journal paper on something that is actually one of the topics on which research is more fervent. So adaptive control, is that right?
Yes. So I'm eager to retell this anecdote, which
please.
Is maybe Peter's favorite. But let me just first say about this environment that Peter and Alan Laub were creating. Alan Laub was the president of the Control System Society at that time.
Yep.
So Peter moving from Illinois to Santa Barbara, it was not obvious at that time when I followed him as his first student to join in Santa Barbara. But that ended up being an event of historic significance in our field. And the evidence of that came later. You know now that there are people like Andy Thiel, Joao Espana, Francesco Bullo, Bassam Bamier. You've interviewed many at once also. Mustafa Kamash, they all moved several years after I graduated. So Peter and Alan had created this Center for Control Engineering and Computation. And it was very important to Peter that engineering be a part of this name, that is the DNA that he had and wanted to calculate. They created numerous courses, linear, nonlinear, adaptive, robust, system ID, and optimal. There were incredible teachers there like Mohammed Ali and Ian Rhodes, from whom I learned so much. I blame them for my obsessions later on to do things right in many domains and to do things conceptually motivated by how clearly and elegantly they introduced the fundamental problems in control systems. It was Peter, really, who was bringing as seminar speakers one big name after another every week, top people in the field. And not a chance for hearing them, but also a chance for us students meeting them. I remember very early on examples that stuck with me showing David Main, my first result, of which I will tell you in a second, showing David Main my first result and a trick that I had come up with to solve a certain problem. And David's response to that was cunning. I had no idea what that word meant in English. I barely knew what many other basic words. I asked him, David, would you please spell this for me, and so I can look it up? So cunning turned out means dexterous or crafty. It was a compliment. They were not always compliments. I remember a discussion that I could not win with Stephen Boyd about whether adaptive control was even a well-posed problem if noise is left out of the consideration. And in that environment, I developed many friendships with Rodolphe Sepulcher, for example, whom you interviewed, Mirjan Jankovic, Randy Freeman, and so on. So let me mention this anecdote that means so much for the entire rest of my career. So I'd arrived sometime in the mid or late summer in Santa Barbara, and this is the time when Peter Kokoruch usually goes to his cabin in Idaho, and he had left. And there were some papers that I knew I should take a look at, in which the research on adaptive control had begun by Peter and Yanis Kanellakopoulos and Steve Morse. And I saw that things were successfully designed and stability achieved for nonlinear systems with parametric uncertainties without any growth bounds. But there was one thing that they were doing, which was reducing the adaptive control at each step of this recursive procedure to scalar problems and introducing a new parameter estimate with each scalar state, which seemed to me just aesthetically irksome. So I thought there's got to be a way, if there is only one parameter vector, to estimate it with only one parameter vector estimate. I started looking into this, being left to do nothing while Peter was vacationing in the Grand Tetons, and then realized, well, this is actually hard. That's why it wasn't done. But I think it can be done. And after a while, I figured out how. Peter returned. He asked me, did you spend a good time off? Did you, go for explore California before the serious thing starts, the classes and so on? I said, well, not much really. I was looking at this problem and I don't know if it's relevant. I showed him, and Peter's reaction was, what? But do you know that we had all tried this already? Me, Yanis, Steve Morse, Marino, Isidori, Shastri. This is a pretty big deal. Okay, this is getting submitted to system and control letters. So I don't have to explain what that did to my confidence from that point on, and what that meant for the goals that I set for myself.
This is so cool. Super cool. So the paper that we are talking about will be obviously linked in the description. It's titled Adaptive Nonlinear Control Without Overparameterization. If I can maybe try to summarize it for those that are not familiar with nonlinear adaptive control, basically in this paper you find a very clever way to employ exactly P estimates for P unknown parameters and significantly reducing the controller order, basically, the order of the dynamic controller. And this has implications for basically reducing the complexity of the controller order. Is that right?
That's right. Mm-hmm.
And the basic technique that is used here is that of backstepping. Is that correct?
That's right. Mm-hmm.
Okay, so maybe we can spend a bit of, some time, not necessarily too much, but I think it's nice for the audience if we spell out what backstepping is, because it seems to have played an important role also in your career.
So backstepping was born out of the single perturbation concept, in which the actuator dynamics would be faster than the plant, and the problem would be treated in such a way that the actuator be modeled by a static map. However, that carries many consequences, including preventing the stabilization from being global. So in the late 90s, various people looked into how to deal with actuator dynamics in such a way that stabilizing a system with actuator dynamics treated as dynamics does not result in results that are only local. And the idea was somehow in the air. If you ask me who invented backstepping, the answer is very difficult. In parallel, there were various papers in which backstepping was present either explicitly or implicitly. Those are papers by John Signas at the National Technical University of Athens, a mathematician. Burns and Isidori, Sontag and Sussman had a paper, Dan Kodicic had a paper, and so on. But it was turned into a recursive tool for systems with uncertainties. All of this was without but it was turned into a tool for systems with uncertainties by Yannis Kanellakopoulos, Peter, and Steve Morse.
And I guess this method applies, I cannot claim to be an expert. I did study nonlinear control at some point in my life, but this applies to systems that are in a strict feedback form. And then basically this is a recursive procedure for stabilizing the origin of a nonlinear system. I'm just trying to create context for the audience. Would that be a fair description?
That's right. Systems in a strict feedback form include many systems: vehicles, robotic systems, fluid systems. Not all systems, but among the various structures for nonlinear control design, this has been by far the most ubiquitous to be found. And often when we write papers, we treat each block as scalar because it is self-understood that if the blocks have different dimensions, such extensions and multi-input extensions are possible. The question is, can you progress through integrators of dimension 1 or possibly more?
I have two comments and I'm happy to move forward afterwards. But so maybe one is an example for the audience. I was thinking of maybe a two-link robotic arm that I guess that would apply as a system in strict feedback form, right?
That's right. And the question is, do you have actuators at both joints? If you do, then the situation is simple. The kinematic equations have the velocities as the inputs, and if the velocity could be applied as the input, the task would be solved, but the actual input is some torque, so you have to backstep through that extra integrator and control the system through acceleration. And that is precisely what led me into control fluids, which we'll talk about later, I presume, because I was quite dissatisfied with applications in which backstepping boils down to being performed only in one step, while conceptually it can be performed in an unlimited number of steps in the theory that we had already developed.
I'm actually very excited to talk about that part. Just want to try to do justice also. The second comment I had was to create context also for our audience. So as we mentioned, you are in Santa Barbara in the early 90s. And that I would say is really the golden age of nonlinear, adaptive control, nonlinear, also trying to make it robust. I guess we'll talk about that also in the episode. From this first paper that we mentioned, then you're basically going on a roll. You win the most important prizes at the ACC, the American Control Conference, and the CDC, the Conference on Decision and Control, for 2 Best Paper Awards, as I mentioned, during your PhD. And at the end of it, you also win as a single author the Axel B Award for a paper focusing again on nonlinear adaptive control, which I find mind-blowing. And also I should mention that your PhD thesis is then turned into a book that is now goes under the name of KKK, or the acronym of KKK, the book that you wrote with Kanellakopoulos, Peter Kokotovic, and yourself, right? And I'm just curious about how was it to live through that period of time from your perspective?
So thank you, Roberto, for putting in the time to study all this. So there are 2 elements to all these various papers. I had not understood myself that early, but after decades, finally I have, that there is an element there of being extremely worried that there is another way of solving a problem that I had missed, because this is conceptually very unsatisfying. If somebody was really, really teased into philosophical thinking in high school, that's an indication that just one solution might be a very misleading high-level perspective on a subject. So I was exploring other ways and finding fundamentally different other ways to solve the problem that I had solved in the fall of 91. So there were the results on so-called nonlinear swapping, modular designs, adaptive control Lyapunov functions, sort of high-level perspective on all of that, the study of convergence to destabilizing controllers and all that. And this was a time of a lot of interest in this kind of research. And Peter was an incredible mentor, a mentor who got out of me more than I ever knew I had. And also, if he hadn't done anything else, he had somehow given me this impression that what we were doing was the most important thing in the world, which I bought. But I think that he genuinely believed that himself. And that was a combination of circumstances that led to that led to the dissertation being recognized, a couple papers being earning some awards, and finally that book from 1995, for which I have to say, the parts that people like in that book are the parts that Peter and Yanis wrote. The accessible, beautiful, intuitive parts, the parts that are complicated, that are conceptualizations of what's in the complicated parts, and so on. That's the stuff from my dissertation.
I didn't mention the titles of the papers, but there will be links in the description of the episode, obviously. One is Adaptive Nonlinear Design with Controller Identifier Separation and Swapping, where you talk about this swapping method, as you mentioned. Then a paper on modular designs that allows you to separate control and estimation to enhance robustness and basically the flexibility of the method. And the book that we just mentioned is Nonlinear and Adaptive Control Design. Absolute joy to read from my perspective. Obviously, one of the most cited books in control. To best of my knowledge, I think it's probably ranks second after the LMI book by Stephen Boyd. And I'm just wondering, so after this wonderful period of your academic career, it's, I guess, 1995, and you're ready to move on to the next chapter. How was it for you?
So it should have been easy, right? In fact, after the first 5 or 6 journal papers, Peter already encouraged me to start applying for jobs. So that was about 2.5 years after I had started. So he suggested me to a couple of places, and I applied to a few places. My first interview was at Princeton in the winter of 94, so 2.5 years after I had started. I think I could barely speak English. I didn't get that one. That one was lost to Vince Poor, who within a few years would become Dean of Engineering at Princeton. There was also an interview at Caltech. I lost that one to Jerry Marsden. But there was also a number of other places where my resume resulted in an interview: Carnegie Mellon, University of Southern California, Illinois, Purdue. But my seminar did not materialize into an offer. I mean, I was interviewing and nothing was happening in terms of job offers, in spite of all the paper awards. The name having created a buzz, the dissertation award, even a book. None of that seemed to matter. I was pitching theory, and people already were theorists and knew how hard that is to pitch outside of our community into grant agencies and so on. I was quite desperate, and at some point I thought, out of desperation, that let me change the approach. Instead of talking about these nonlinear extensions of adaptive control, instead of talking about the fundamental advantages of adaptive control over robust control, which some people really responded to well. I remember John Doyle being delighted for these differences to be quantified. I thought, okay, I'm interviewing in the mechanical engineering department at the University of Maryland. Definitely pitching the theory will not result in a different outcome in this environment. But there was a project at UC Santa Barbara which Peter Kukorovich and Art Krenner and Richard Murray and Carl Nett, at that time from United Technologies, had won from the Air Force. It was a project on control of jet engines. And I had done some work on that project. And I thought, how about I speak to mechanical engineers about the control of a jet engine instabilities, rotating, stall, and surge? And how about I explain physically what the problem is, because not everybody knows this phenomenon, and then show the solution. That was an instant job offer. Then, okay, taught by that lesson, I did the same thing at UCLA, and the next job offer followed. I decided to go to Maryland for some reasons, and finally a relief happened in the form of a job. I started at Maryland in the summer of 1995. Again, mechanical engineering, you're beginning to see a pattern that my first exposure was to mining engineers, which are mechanical, then again mining engineer, and being forced by the circumstances to stretch myself across different fields. This was a blessing in disguise. As an electrical engineer, I kind of became some sort of a mechanical and aerospace engineer, and applied math was always there in parallel.
I think it's very difficult to put you in a box, but as you say, after this PhD period, you start being exposed to many different things, particularly the use, I guess, of PDEs, but also I see in the records also a stochastic stabilization episode. So the application of the backstepping method that you mentioned before to stochastics. I don't know, where do you want to go from here? Because it seems like there's way too much meat on the grill.
I can tell you about this. This was, for me, a very exciting episode. Not because I ever wanted to become a stochastic person, but I could not resist staying completely out of it. So just as I was finishing all my work on adaptive control of nonlinear systems, my office mate and friend Randy Freeman was finishing his work on robust control of nonlinear systems. And there was a book by Randy and Peter in '96 on that. So adaptive and robust had been done, but nothing stochastic. Certainly nothing stochastic on stabilization. And nobody taught stochastic control at UCSB. Peters is just not a stochastic. That's not his direction. But at the same time, linear H-infinity control has transitioned into many efforts in nonlinear H-infinity control by Isidori, Bashar, Bill Helton, John Barris, and so on. And nonlinear H-infinity was being explored at that time, and an analogy was observed with stochastic risk-sensitive control. So that really caught my attention. There are all these other nonlinear people looking at control from the stochastic direction. I had acquired no tool to enter that subject in Santa Barbara, but there was a graduate course in Belgrade that a very strong professor, Srđan Stanković, taught. And he taught out of two books, Jasinski's book, from which I learned the Ito calculus, and Astrom's book from 1970, from which I learned the elements of stochastic, at least linear control. So I put time into that. The most fun thing was the Ito calculus, the fact that all of a sudden the Lyapunov stabilization needs to take care of second derivatives of the Lyapunov function, as if the first derivative wasn't hard enough. So this was a challenge natural for somebody in their 30s to pursue, and I put time into that. That was the start, stochastic backstepping under multiplicative noise, which is not equilibrium destroying. But then I observed that the typical noise in linear systems is additive. And the noise in my first work was treated only as a nuisance, not as an input, and not in any other work out there. So the noise, to be regarded as analogous to a deterministic disturbance, needs to have an unknown bound. In other words, the covariance needs to not be known a priori, but treated as an unknown time-varying signal. If we were to truly have an analogy between robust deterministic control and robust stochastic control. So I got to that conclusion by reading carefully the book of Green and Linebeer, Ostrom's stochastic book, and so on, and came up with something called noise-to-state stability, which is a stochastic form of Sontag's input-to-state stability, except that the disturbing input is not the noise itself, but the intensity of the noise, the covariance, and everything gets developed in probability and so on. And it was an episode because I never wanted this to be my profession, but, I wanted this experience.
It's incredible. I think it's also, I can fairly confidently say that it's a very tough subject on its own. I actually looked into the relevant papers. Again, just for our audience, the first one that we mentioned is from 1997, Stochastic Nonlinear Stabilization 1, a backstepping design with Hua Deng, and also with the same author, but also together with Ruth Williams, also from UC San Diego. The second paper is called Stabilization of Stochastic Nonlinear Systems Driven by Noise of Unknown Covariance. I find particularly cool the idea of not having a bound necessarily on the noise covariance, which is, I would argue, is a standard assumption in stochastic control. I just wanted to give our audience also what do we mean by stability in the context of a stochastic system. So I think here we're talking about global asymptotic stability in probability. Around the same time, more or less, so around the 1997, 98, those years, you not only develop an interest in stochastics, as we mentioned, but also in partial differential equations, which is definitely one of the topics that makes you most famous for sure. I'm just curious, How did that happen? What has drawn you to PDEs?
By that time, I had moved from Maryland to UC San Diego. This was the result of not just publishing my second book and getting some attention through that, but I published some papers with industry, demonstrated that I'm not just limited to theory, and then I didn't have to apply for jobs. I was, from even some of the previous places, receiving calls to apply, and the one place that both my wife and I liked as our destination was back in Southern California, San Diego. So I moved there in 1997. That was after 2 years at Maryland. They hired me with tenure, with 2 years after PhD. And it was an academically exciting move because it was a department that was top 10 in mechanical and aerospace engineering, full of absolutely leading people in fluid mechanics and combustion. And I had just done some work of control of all of that. But this was a moment of kind of a creative crisis because I felt that everything that I had done up to that point had been on subjects in adaptive, robust, and stochastic control, which were almost unexplored, or for the most part unexplored, and what was left wasn't of that kind. The canvas has sort of been filled for the most part, and the detailed brushwork was only what was to follow. This was a creative crisis, and I also felt that, just to use a vulgar word, almost a bit like a fraud, because, all these n steps of backstepping, I was finding them as being needed only with n equals 2 in robotic systems, and maybe n equals 3 if we incorporate the motor dynamics. But what about, n greater than 3? I wasn't seeing any such systems. But then finally I realized, those systems are in fluids. I've already seen them in the ODE representations of fluids for compressors and combustion instabilities. There is backstepping not only of dimension n, but of dimension infinity if you look into fluids, if you look into PDEs. But there was one thing that I didn't like about, or one thing that I found scary about working in fluids. Everything that led to ODEs was the result of model reduction that fluid mechanicists had to develop properly, something that I didn't have the background in, and these model reductions were career-long pursuits, not something that somebody will produce for me in a week and then I go off to design nonlinear controller. So I realized at the same time that I need to go into fluids and that I need to look into PDs. So the first attempt was inspired by an infinite chain of integrators, which doesn't converge, doesn't work, and that was a big surprise, and it demanded a different customized approach, and that approach ended being the approach using Volterra operators. So that's how I got into control of PDs. The fluids objective was yet to follow, but one first had to look into PDs of basic classes, parabolic heat equations with reactions, and so on. Various unstable problems. That was the point. The problems need to be unstable. There was a significant bit of luck that a particular student applied to me at that time from the Moscow PhysTech. They're sort of the MIT of Russia, as they would call it, Andrei Smishaev. And Andrei's math was off the charts as an engineer. And Andrei somehow connected with my sweet spot, my preference for getting the results that are not only of the existence type, but with explicit solutions in some cases. Because to me, interpretation of results is crucial. Just giving a direction to the designer and not being able to explain in retrospect why what's obtained makes sense wasn't satisfying. So Andrei was a crucial partner at the beginning, and explicit solutions were a crucial element of producing adaptive controllers for PDs. So that part, the initial part of work on developing PD backstepping, I would say that the climax of that is a certain book that Andrei and I published, a textbook published by SIAM in 2008. That was important because it won the Chessbook Textbook Award, and also it's important because how unintentionally it developed. So I wanted to teach a class on PD control with an emphasis on backstepping so that my new students are prepared. But of course, I would like other people to learn PDE control. And there were undergrads who wanted to take on PDE control. These are mechanical engineers. They see structures, they see fluids, they see combustion. So I had this class, which was a mix of my specialist PD, PhD control students, other PhD control students of other faculty who aren't there to be taught things in an abstract way about PDs, and then undergrads who come with a really good feel for these things, but not mathematical, not much taste for abstractions at all. So I had to keep this course physical and mathematically intuitive. It seems like a mission impossible. And I was pursuing this mission in real time, one lecture at a time ahead of class. It was sort of like an adaptive MPC with a very short time horizon. I was identifying my class as I was controlling it and feeding it. And I was very satisfied with how it went, because it was an approach with a lot of attention to how the material is being absorbed. So anyway, the class was over. And after the class, two of the PhD students who were not my PhD students, Matthew Graham and Charles Kinney, tell me, hey, we've typed up all of your class notes. I didn't have class notes. I was sketching things by hand on my notepad the day before lecturing, and they showed me the class notes. And this looked really had worked out quite well. These two men, Matthew Graham and Charles Kinney, are now quite distinguished engineers in ASML in San Diego. So I said, Matt, Charles, would you mind if I expand on this and treat this as a textbook? I think it would be very useful, because I had also taught this course at Berkeley and Santa Barbara in the meantime. So Andrea and I wrote this book. It came out. It was modest, 180 pages, because that is what you can cover in 1 quarter in the UC system, and it has had a very good reception. It's been the entry point for just about everybody who has gotten into the subject of PDE backstepping. It has 2,000 citations. And yeah, that was sort of the point at which I thought I had completed my first efforts in PDE backstepping.
So many questions from here, and incredible, obviously, to follow your thought process. I guess the book that we were talking about just now was Boundary Control of PDEs, a course on backstepping designs, as you mentioned, written with Andrei Smyshlayev, probably?
Smyshlayev in Russian means the thinker.
The thinker. Oh, wow.
Yeah.
So cool. Definitely nomen omen, as the Latins would say. So definitely I would like to make a few pointers for our audience. First of all, the papers that one of the papers that we talked about before, I believe, is closed form boundary state feedbacks for a class of 1D partial integral differential equations. So actually, these are even more heavy duty beasts, I would say, because they're not just partial differential equations, but they're partial integral differential equations. So there are integrals as well involved in the picture. As I was reading the paper, I was particularly fascinated by it because, as you say, there are explicit solutions for explicit feedback laws for these type of problems. And that essentially avoids, to the best of my knowledge, the complexity of solving operator Riccati equations rather than, as I mentioned, just applying an explicit feedback law. And I found also particularly fascinating this discussion on the inverse optimality of these control laws. I don't know if you want to comment on those, or should we move forward?
That's a lot of things. I would say that, I want to be brief. Inverse optimality is very interesting and important. Maybe we can get to it later if we talk about inverse optimal safe control. But these solutions, these feedback gains, whose solution doesn't require the solution of abstract infinite dimensional operator Riccati equations, that's the key. What was beautiful about how the PD backstepping approach worked out was that to find the gains, instead of needing to solve quadratic infinite dimensional equations, you had to solve a certain class of PDEs. And this class of PDEs is called the Gursa form PDEs. These are PDEs that are hyperbolic, but with a space growing along with time. It's a class of PDEs that is really interesting, and to my knowledge doesn't arise in any other domain. It just popped up in control theory. And it turns out it's a class of PDEs that is solvable by a conversion into integral equations, and those in turn are solvable explicitly or nearly explicitly with successive approximations. So we struck something really intellectually stimulating in addition to it being useful.
Super cool. Also for context, I thought it was nice for our audience to classify what we mean by, I believe we're going to talk about several types of PDEs. It would be nice to classify PDEs by these adjectives that we've been using casually so far. So we talked about parabolic PDEs, hyperbolic PDEs. I think it would be nice for the audience to give some context for what these terms means and maybe some examples too.
Thank you. I will give some very crude definitions. The mathematical definition is much less informative than the engineering or intuitive interpretation. So the hyperbolic PDEs are in principle the simplest PDEs. They contain one derivative in time and one derivative in space, or in each of the spatial variables that might arise. The more important thing to see is that the dominant physical or engineering phenomenon is transport, as the physicists would say, or delay, as we, as electrical engineers, would say. If there are additional things, they can actually... so the key feature is that such PDEs need not necessarily be distorting the input applied through the boundary condition, but they may, and they may be unstable. The parabolic PDEs have one additional derivative in space. So they're second order in space and first order in time, and they may have some additional features like reaction and advection and so on. The dominant phenomenon of the second derivative in space combined with the first derivative in time is the smoothing of the solution in space. To an electrical engineer, that means low-pass filtering. The low-pass filtering of the most severe kind. Imagine a low-pass filter with infinitely many poles which get bigger and bigger and bigger. So this is a phenomenon that really, really kills high frequency in time and space behaviors, but doesn't exclude instability. Things still can grow.
Great. And so I guess for the, as an example for hyperbolic PDEs, I can think about the telegraph equation, I believe. Is it called the telegraph equation?
Yes. And from the telegrapher equation to stop and go instabilities in traffic, there are a few steps, but it's the foundational mathematical phenomena are shared.
Which I definitely hope that we're going to talk about later also, because I do have an interest in traffic lately. And instead for the parabolic type of equations, I guess heat equation would be one example, right?
Yeah, anything thermal, but thermal alone is not destabilizing. If you have, in addition to the thermal convection, some energy production through possibly chemical reactions, this can actually go unstable.
Fantastic and extremely fascinating. Of course, I mean, from my perspective, what I see in the records is that then you start exploring all sorts of phenomena described by partial differential equations. And I would argue that the queen partial differential equation, or the king, I don't know what sex we want to attribute to a partial differential equation.
Queen.
The queen is definitely the Navier-Stokes equation. And you did some work on that too, right?
Yes, thank you for making time for this particular episode. So, I first saw control fluids in a seminar by Jason Spire in 1995, before I had even left Santa Barbara. He gave a talk at UCSB. That was pretty fascinating, but I had no idea that that was in my future. Simultaneously, as I was realizing that I need to start looking into PDEs, the subject of flow control was peaking, with the peak being somewhere around 2000. Not just Jason Spire, an aerospace engineer, but Parviz Moin, a top fluid mechanicist at Stanford, Phil Holmes, who then might have been a dynamical systems person, who might have been at Cornell at that time, then moved to Princeton. Roger Temam, a leading French mathematician. They were all looking into flow control and turbulent Navier-Stokes. Indeed, the holy grail of among PDEs, both in classical physics and in mathematics, or at least applied mathematics, the so-called $1 million question. I was still young. It's now embarrassing to look back at the vanity of my thinking at that time, but the thing that I had that they didn't was control and feedback. So it seemed to me, I had this dream of impact that while we can't establish the global existence and uniqueness of solutions of Navier-Stokes in open loop with feedback laws, with PDE backstepping feedback laws, that $1 million question might be answerable. I hadn't yet started working on them, but already had a student who had arrived and ready and super talented, Rafael Vasquez from Seville. And it's embarrassing to what I might have said. I'm not sure I remember it correctly, but it amounted to telling Rafael that in his PhD alone, he might achieve scientific immortality if this problem turns out to be solvable. I was actually wrong in this intuition. Global stabilization with boundary control turned out to be impossible even for the Burger's equation. And this was proven after Rafael and I tried and couldn't get global, but only local. But we achieved local stabilization of Navier-Stokes equations at arbitrarily high Reynolds numbers, namely at arbitrarily high levels of instability or turbulence or chaoticity and so on. And also for magnetohydrodynamic flows, namely for electrically conducting flows in magnetic fields like plasmas, which also might be turbulent. So that's that episode, and it constitutes my lowest ROI, my lowest return on investment result. And I don't mean just in terms of citations. I just mean in terms of how much it has impacted the field, how ignored it has been by fluid mechanicists, control theories, and so on. Maybe it's still a result that's ahead of its time, but within the finite time lifespan, one observes how much work has gone into it and how little difference it has made.
Fantastic. Obviously, this makes me extremely excited to talk about it. I thought it would be nice to, give some context to our audience here too. We may have talked about the Navier-Stokes equations at some point in this podcast, but maybe it's better to do justice to it by just saying that this is one of the most fundamental PDEs describing basically motion in compressible fluids. Please correct me if I'm wrong, Miroslav, because I'm not an expert. And we were chatting offline also about the meaning of what it means, what the Reynolds number means.
Yeah. Mm-hmm.
This is a dimensionless quantity that basically indicates the flow regime in this fluid. Low Reynolds numbers means laminar flow, as they say. So basically very viscous fluid, and high Reynolds numbers instead mean essentially mixing in turbulence or the inception of turbulence, if I understand correctly.
That's right. Fluid mechanical systems can present so many problems based on both the Reynolds number and based on the geometries in which the flows occur. Fluid mechanicists have, I think, reached an agreement that the problems to be studied fundamentally should be geometrically as simple as possible. And this is why those who want to understand turbulence in the purest form actually study the channel geometry, in which the turbulence arises purely from the interaction of the flow with the wall and from the flow speed, the net flow speed, or the net pressure gradient driving the flow speed being high. They're, of course, super interesting and exciting looking flows in complicated geometries, from as simple as a flow around a cylinder to a flow over a full-blown aircraft. But at the scientific level, simple geometries like the channel flow are the geometry against which new concepts are measured. So that is the geometry in which I invested the largest amount of time. One should say that the Navier-Stokes equations are nasty for a mathematician and for a control theorist because they're actually algebraic differential equations. The fluid mechanicists package them elegantly through the divergence-free condition so that you don't see this nature. But as a control person, when you look at them, when you solve for the pressure, when you substitute the gradient of the pressure into the Navier-Stokes, you see that these are incredibly complicated equations in whose right-hand side integrals in space appear. And that gets us to those integrals in the partial integral differential equations that you mentioned 5 minutes earlier in the work with Smyshaev. Those things aren't there just because one can handle them, but because they arise.
Extremely fascinating. I guess we didn't mention the titles of the papers, but again, there will be link in the descriptions. One of these is a closed-form feedback controller for stabilization of the linearized 2D Navier-Stokes Poiseuille system. That's the flow in a channel pipe, right, under constant pressure.
Yes.
Okay. Extremely fascinating. I just had a curiosity in reading this paper, because when you essentially develop these control laws, also in explicit form, you have to use different norms to prove exponential stability. I know that this is an extremely technical point, but I was curious about why one has to use different norms, let's say L2, H1, H2, in order to express the stability concept.
Yeah, control people can easily understand that. There is no norm equivalence in function spaces. You can have very sharp peaks that make L2 norms finite, even infinite peaks. So you can't say that you've established a property in the spatial L2 sense and be sure that the state is bounded. So then you have to go, you want a result in the spatial L infinity sense, but that's not a natural Lyapunov function. So then you have to go into a space that bounds the spatial L infinity space, and that happens to be the Sobolev space H1, which is nothing but the space endowed with the L2 norm of the spatial derivatives of the state.
Makes sense.
It's not something to be regarded as just revolting. It's actually beautiful because it is so commonly present.
Yeah, it's essentially a natural way to quantify stability for that type of partial differential equation.
Yes.
Very fascinating. I mean, this is going to make me read a bit more in depth those papers after this conversation. Very, very cool. And then, okay, as I mentioned, this is not the only type of PDEs that you look at in the course of your academic journey, but there are many other types of PDEs. I think so far we didn't talk about hyperbolic PDEs that essentially govern how we model traffic, at least at a macroscopic level. I'm curious, how did you develop an interest in that subject too?
So I was growing very frustrated after about 10 years with parabolic PDEs, that I had nothing to say on hyperbolic PDEs. And I was surrounded by people who were talking about hyperbolic PDEs, engineers primarily, Alex Bain at Berkeley, various French researchers, bringing traffic problems to my attention. And I was looking at these models and I had nothing to say on them because they didn't call for stabilization. And the French were owning all of these flowing systems in one dimension, traffic flows, water waves in canals, instabilities in oil drilling, and so on. So it took me a while for somebody to draw my attention to the so-called all-Russell model of traffic, which happens to be not the first-order model with only the density state, but a model in which the velocity is not represented as a static output, but as an independent state. So truly a set of two coupled first-order hyperbolic PDEs rather than only one. And it is only in that kind of a model that instabilities arise, and there is something to do for somebody like my students and me. So once we turned our attention to that model of stop-and-go instabilities in traffic, lots of theoretical effort happened. And it's interesting how it started. Jean-Michel Courant and Georges Bastin came up with a design for the first benchmark configuration of coupled first-order hyperbolic PDEs at the same time as Rafael Vasquez and I did. I remember to give a talk in some workshop at the Institut Henri Poincaré in Paris some years ago. I don't remember the year. And Jean-Michel telling me, you know, we've given a try to backstepping. I want to show you what we have. I want to show you some equations. And he sends me that evening an email. And I realized, oh my God, this is a solution that Rafael Vasquez, with different notation, sent me maybe a week ago.
Wow.
I show up in the morning and say, Jean-Michel, I hope you will believe me that this document was not the result of you sending me yours, but it really happened concurrently. And these are wonderful people. And of course, the solution was found within 60 seconds that we published this together.
So cool.
And that's how it started. This enabled then many, many extensions to multiple coupled hyperbolic PDEs and so on. But traffic is to this day the most relevant application domain, which everybody can understand. Everybody intuitively grasps both the model and the feedback that does that. And the point of the application to traffic is not that you apply a controller at every car, but that you apply a boundary control, namely that you apply control only at a ramp. And the most interesting case is when you apply control at a downstream ramp and want to control and suppress the oscillation of the cars heading towards the ramp rather than downstream of the ramp. It looks almost impossible. That's why it's so exciting.
I definitely share the excitement. When the first time I saw it, I couldn't believe it that these type of models actually are well suited to model so-called traffic waves, stop and go waves. Mm-hmm. There's plenty of videos online. Maybe I'll link one also in the description for those who don't believe it yet. But traffic waves do exist, and macroscopic models offered by partial differential equations essentially work very well. I just wanted to clarify what it means for our audience. What is essentially ramp metering? This is one typical form of control for, let's say, traffic flow in a highway and variable speed limits too.
Yes. So ramp metering we see at many on-ramps in San Diego. They usually come with the constant lengths of the red and green lights. The idea in applying feedback control is that the length of the red and green lights would vary in order to stabilize the traffic. Variable speed limits are the recommendations that you see above the freeway that tell you what's the speed limit to drive at. And that form of actuation is necessary if you are controlling multi-lane traffic. You just cannot dictate the speed of different lanes with ramp metering alone.
Fantastic. And this is also one of the very concrete applications of control that actually changed the way we live. I believe that Americans alone are spending 72 hours on average in traffic every year. And just through the application of these methods, basically we can reduce discomfort and also do something good also to the environment. And then I see that from this moment onwards, something I would say radically new in your academic interests arises, and that is the topic of delays. It seems like you're going progressively from something that is very hard to something that at least apparently is easier. And I'm curious to understand, why did you develop an interest in this subject?
So 2 reasons. First of all, you have to imagine not the status of acceptance of PD control at present, but the status of acceptance of PD control in the mid to late 2000s. It's a very, very niche topic. We're working very hard. There's barely anyone who understands us. The students need jobs and so on. So one ought to step away from niche subjects into subjects that are more broadly understood. The other factor is that I got to some point by working on hyperbolic PDEs to a result that happens to recover a certain solution in predictor feedback, not Smith predictor, but another form of predictor feedback, which follows as a corollary, as a very special case of controlling hyperbolic PDEs coupled with ODEs. And I'm fascinated with special cases which lend themselves to interpretations. This is a reward, being able to interpret. It's a reward for working on a concept. And I always prefer to see the simplest and clearest manifestation of a concept over the most general manifestation of a concept. So that's what drew me into systems with delays. My students were busy working on PD control. Vasquez on hyperbolic at the time, Smyshev on parabolic, and so on. I had to take on these delays myself at that time if this were to be done. So I went into being a nonlinear control person. I went into extending these predictor concepts which were developed for linear ODEs to nonlinear PDEs. And this resulted in a single author paper in 2010. I had a collection of results along that line at that time. And having satisfied my thirst for saying something on delay systems and predictors, I did what I often do when I want to move on from a topic and have plenty to say on it. I thought, okay, the way to put a period and move on is to write a book on that subject and get to another thing. So I sat down to do that with a plan for a 200-page book. But here's what happened. These delay controllers resulted from the PD perspective. And the obvious question comes, what if instead of having an input delay, you have a PDE at the input or a PDE at the output? What would the result be? I mean, can I really just pose this question and not put the time into answering it? I could not. I could not stop. So that 200-page book plan grew into a book of 470 pages, and that book has a ton of different things. It's more a book of ideas than a book of comprehensive solutions, and it has served the role that I was hoping. It has seeded many, many ideas which have now branched into, I would say, not just many results, but many careers beyond my group. This whole delay subject comes with a few anecdotes that I might share with you.
Please.
So Nikos Becharis Liberis, that is the name of one of my most talented students, he generalized these predictor feedback results to systems with delays that are not constant, but depend not only on time, but on the state. And that's a really hard problem because the state you don't know a priori. And you have to compensate the delay over horizons that you don't know a priori. Really excellent results, and we published those many, many results as a book in 2013. But I want to say something about, don't judge a student based only on his results. There was already an early indicator. When he was applying to me, he asked me, what am I working on? And I said, well, I work on PDE control, and this book is just about to come out with time. And if you want to look into this and decide whether you want to apply, here's the PDF. So within, I don't know, maybe a month, maybe 2 months, Nikos sends back to me the solutions of all of the, 50 homework problems, which some are not routine at all, to that. And we already had a solutions manual. I'm looking side by side, and every single solution is correct and elegant. So, okay. And he's now building a really fantastic career as an ERC grant recipient at the University of Crete. Another exciting story is with Delphine Bresch-Pietri. She was sent to me from École des Mines by Nicolas Petit as an advanced undergrad. And she arrives and I ask her to do some simulations with delay adaptive control of PDs, the subject that I wanted to do because I work on delays and I have an adaptive background. I had developed some controller. The stability analysis I had conducted only mentally. I knew that it's possible, but did the calculations while driving or, being away from a notepad. I knew it was possible. So I asked her to do simulations. She sends me back simulations with several lines of some expressions that I thought, oh my God, I'm working with undergrads. What is this nonsense? Then I look more careful into this. Turns out these are the estimates that I expected would be possible, but the calculations are so complicated that the results are unrecognizable, not instantly recognizable as correct. Again, an indication of talent, and you probably know Delphine as a professor at École des Mines now. A third story with a student that indicates both talent and character was when I moved on from working on cascades of delays and ODEs into cascades of parabolic PDEs and ODs. And the canonical such cascade is the so-called Stefan model of phase change. This is the phase change between liquid and solid. It's a very difficult PD because of a moving boundary condition which is governed by a nonlinear OD. So I mentioned in a group meeting that this is an open problem. It's a great problem. I think I was just speaking to myself. I was not suggesting it. Schumann, whose background was in physics and he wanted to do something combining information theory with nonlinear control, comes to me several days ago and shows me a result. And my intuition says this result cannot possibly be that way. It can only be a local result. And I ask him, you're saying you've got a global result here? He says, yes. I said, Schumann, okay, why don't you consider another problem? I mean, this was at the moment the best way of saying, this is hopeless. He insisted. He took me through the details, and I realized that something very special arises in that class of PDEs with moving boundaries thanks to a principle that doesn't apply in other PDEs, thanks to the so-called maximum principle for parabolic PDEs. His result was correct, and his personality and confidence was strong enough to overcome a pretty significant degree of advisor discouragement.
Amazing. I enjoyed every single story. I guess the book that we were referring to is called Delay Compensation for Nonlinear Adaptive and PDE Systems. This is the first book on the subject, if I am correct.
Mm-hmm.
And since we mentioned it, but just to give context also to our audience, I think it would be nice to clarify what we mean by the Smith predictor. For those who have studied control engineering, I think almost everyone should encounter it at some point, but just to be sure, I think it would be nice to specify what that means.
What Smith predictor means or what predictors mean?
What the Smith predictor, but also predictors, if you wish.
So the Smith predictor is a particular form of a prediction that is applicable only to stable systems. The predictors that we're talking about here apply to general systems that are possibly unstable. And the concept for linear plants is extremely simple. You can predict the future state using the variation of constants formula for LTI systems, treating the current state as the initial condition and treating the past inputs as an input history. And you get the formula for the future state, for the state at the time when the control being applied now will hit the OD. You get it in an explicit form. And when you look at this explicit form, it's a feedback law containing the state of the OD currently and the history of the input applied up till now from the time back that is of the length of the delay itself. So it's a feedback law, but it's an explicit infinite dimensional feedback law. You don't get that for nonlinear PDEs. That is the reason why I invested time into these nonlinear generalizations.
So we mentioned a lot of subjects until now. We mentioned nonlinear adaptive control, we mentioned partial differential equations, delays, and yet there's more to talk about, and that's extremum seeking. Because I found, when doing my research, I found that there's this paper from 1997 from you and your student, I believe, Xin-Seung Wang, that basically provides the first proof of stability of extremum seeking, that to that date, I believe, was not proven. So I'm curious about how did you develop an interest in this subject and how did that proof specifically arose?
And this is about going back to 1997. I'm 2 years out of my PhD. I'm at the University of Maryland. I'm working with United Technologies, Klaas Jacobson, Andrzej Banaszuk on control of combustion. And I mentioned to my faculty colleague, a combustion person, Ashwani Gupta, Ashwani, I'm working on combustion control. Maybe we should chat about this. And Ashwani says, oh, I've used combustion control in a certain master's thesis, and he shows me the master's thesis. And I'm thinking, what can I possibly learn from that? He says, look at this. It's called extremum seeking algorithm. I look at this block diagram. It's extremely simple. It has one integrator and a sinusoid. And I look at it with enormous disbelief because I had just written a book on adaptive control of nonlinear systems. What can possibly somebody do with such an algorithm? But what bothers me is that I don't understand how it works. I'm sure it has some limitations, but how does it actually do the limited things that it does? At the same time, I feel a bit of a sense of betrayal that Peter Kokorovich had never mentioned to me such a thing. Then I start reading the literature, and I find out that it's a legitimate topic that was thriving in the 1960s. There was the first discovery in 1922 by a French inventor, Maurice Leblanc. It was hot in the 40s in Russia, in the 50s in the US, and then after the 60s, it disappeared, presumably being rendered obsolete by model-based adaptive control. Fine, but how does it work? None of the literature shows any analysis, any proof of it. That was a challenge that prevented me from doing anything, even sleeping, until I understood it, because it was a challenge by a two-line algorithm to my algorithms that take pages of complexity. And even though they're not addressing exactly the same problem, both are addressing related problems. So I worked until I could finally answer this question and establish not just the stability of the algorithm, but established the guidelines with which the algorithm can be used not only for static maps and optimization of static maps, but for the optimization of dynamical systems that have unknown output maps. And that required the use of two different perturbation methods, the averaging theory and the singular perturbation method. And what was not obvious at the beginning is what was to be fast, what was to be slow. There were three timescales in it. It was not clear how they should be layered. And as my friend Art Krenner likes to say, everything is obvious in retrospect. But at that time, it wasn't at all. People who don't know extremum seeking but are younger and know some of the current trends like feedback optimization. Extremum seeking is essentially feedback optimization, but model-free. Model-free in the sense that the output map or the cost that needs to be optimized is completely unknown and exploration is needed. And there can be dynamics, which also need to be controlled, if not open loop stable, and they may have to be controlled in a model-free or model-based manner. So that is the start of extremum seeking, 1997, that paper, and at present, you see about 20,000 papers that have followed, 3,000 patents. I don't know what branch of industry hasn't tried it. I'm hearing even from the industry on large language models that extremum seeking is being experimented with for adjusting the weights for certain data sets, for example, 20 different data sets. How are you going to determine what's relevant and what's not in a completely model-free collection of data?
Super fascinating. I mean, I have lots of things to say about this subject because I must admit that it was, despite being somewhat, having had a cursory reads on the subject, I didn't have the time to actually look into it a bit more in depth before this episode. So for context, also for our audience, extremum seeking is basically, as you mentioned, a way to find the extrema of an unknown static map in the simplest case, then possibly also reference to output equilibrium map if we want in a bit more general case, in real time and without a model. And the idea is to perturb our measurements with sinusoids to essentially estimate the gradient of this map. And in reading this paper, by the way, the title is Design and Stability Analysis of Extremum Seeking Feedback for General Nonlinear Systems, presented at the CDC in San Diego in 1997. You write, we hope that the proof of stability of the extremum seeking scheme will revive interest in this practically important but regrettably neglected area of adaptive control research. And I would say that it's fair to say that you succeeded very vividly.
I don't remember even writing that or wanting that. I thought it was simply something that I could not ignore, as I then, from that point on, I thought, return to what really interested me, which was PDE control. And I tried to walk away from extremum seeking numerous times, and it just won't let me walk away.
There's a couple of other tangents here that I think I really want to do justice to them, because so far we mentioned many, let's say, theoretically challenging problems and also methods to attack them, but we didn't talk about the, let's say, applications aspects of all these methods. I hope we'll have time also later to talk a bit more in detail about the tension between practice and theory. But I thought a very cool application of this particular method was in photolithography and things that you've been involved very heavily. I think that this anecdote deserves to be told.
So if you don't mind, I would like to get to it as the final part of my answer to this question, because it's the most impressive and important answer. But I would like not to skip over the theoretical advances in extremum seeking and with the practical applications in mind. So as you mentioned, the extremum seeking emulates in a model-free manner the estimation of the gradient and updates in that manner. There are other non-necessarily gradient-based schemes like the Newton extremum seeking. You mentioned that sinusoids are being applied, but there's also a stochastic version of extremum seeking in which low-pass filtered white noise, or if you wish, colored noise, is being applied instead of sinusoids, just another form of a zero mean in a stochastic sense of a mean perturbation, which I developed with the postdoc Shujun Liu with a book that came out in 2012. And this was fascinating. It took one afternoon to come up with the algorithm and develop the simulations. But we are theorists. She's a mathematician. We want more than simulations. How to develop the theory? Turns out that there is no averaging that is applicable to this. So it took 6 months, 8 months to develop the theory that addresses the stability of this two-line algorithm. That was satisfying. Rather than frustrating, it was satisfying. One of the applications of extremum seeking that is really popular is in robotics and even more in autonomous vehicles, and it's called source seeking. So if we think at the modeling level of a vehicle in the form of a unicycle, it would be how to control a unicycle so that it reaches a position where a certain signal is maximal without knowing its own position, without measuring position, or as application people would say, in a GPS-denied environment. There were a couple of solutions with my students that were valid, but not the most practical. But the first really practical solution, where the vehicle just keeps moving forward and it's only being steered without shifting it to reverse and stuff like that, was developed by Jenny Cochran. And this is an interesting story. Here is an MIT computer science student with an MIT GPA of 4.0 and the captain of the water polo team. I mean, quite a capable person who came to UCSD to study robotics, underwater robotics in the Scripps Institution of Oceanography. She takes the class on nonlinear systems and shows up at my door one day. Says, I'd like to transfer to your department. Will you take a student with her own fellowship? Yes, Jenny, of course I will. An A-plus student. She moves into the lab, and I've been talking about this challenge of doing extreme seeking only by steering. Here's Jenny, comes up with a solution, solves this after all the other students have tried. So this was a wonderful beginning of source seeking. There was another major game-changing result in source seeking with a student, Alex Schenker, who is currently a leading researcher in control of charged particle accelerators, I would say, around the world, working at the Los Alamos National Lab, in whose PhD thesis, another approach to source seeking was developed, which turned out, it was proven by another researcher, that it is exactly the algorithm used by sperm cells to seek an egg in the course of fertilization. So this was evidence that the evolution has come up with something meaningful, and we have just provided the Lie bracket averaging justifications for the evolution's choice.
Incredible.
It was also another really interesting theoretical development that led to the so-called Nash equilibrium seeking for non-cooperative agents who are involved in a game. And there's a really nice anecdote about that.
Please.
So Peter Kukotovich was to receive a certain award at Georgia Tech. And this award was going to be marked by a workshop at which several of his closest friends would speak. And those three closest friends were Tamer Bashar from Illinois, Petrosianu from USC, and me. So I'm thinking, what am I to present that's not going to bore Tamer, Petros, and Peter? And my biggest worry was boring Tamer. And I realized, look, Tamer cares about games. He's the supreme authority in games. I think extreme seeking would apply to the game setting. I've never tried it. How about I have the time to work out the duopoly game, just two players with a not necessarily a zero-sum outcome, but competing in a market. And I worked out that, the results, the simulations, and the theory. It was kind of fun that when you're speaking in Georgia Tech in Atlanta, duopolies are everywhere. Coke is there with its rival Pepsi. Delta Airlines is there with its rival United Airlines. So it was fun. And this led from an example, from what I meant to be only an example, to a research direction that we pursued with Tamer and the student Paul Freehoff, whom I had just gotten from University of Washington with a recommendation by Alberto Isidori. There is really one more major theoretical direction that I should not be silent about, and that's the application of extreme seeking to PDEs and systems with delays. And this was developed with Tiago Ru Oliveira from Brazil. And this was an effort where PDE backstepping and extremum seeking, two seemingly completely unrelated interests of mine, had to be merged. But it was really unclear how to merge them. It took 8 complete rewrites of a paper until the order of some half a dozen steps that go into both methodologies was gotten right. And this has been a template for numerous extensions and even a 500-page book that appeared 3 years ago that Tiago spearheaded. So you asked me about the industrial application to photolithography. And that's one of the most exciting things about extremum seeking. There is a company, or there was a company called Cymer in San Diego that was supporting a center that we had started, and at the same time developing an incredible new technology called extreme ultraviolet light, which was meant to reduce the feature size in computer chips from 250 nanometers to 40 nanometers. That's a factor of 18 reduction just in one dimension. And in terms of area, it's a reduction by 2 orders of magnitude. You can just imagine how much denser and how much lower power consuming and faster the chips can get when you reduce the transistor size by an order or 2 orders of magnitude. The technology was incredibly complex. The only way you can produce light with high intensity at 40 nanometers is with a particular process where you use liquid tin droplets and shoot at them with pulses of laser, and that results in an emission of a light at 14 nanometers. This was physics, and it was lab, and it was developed, and it worked in San Diego. And then the shipments started to Taiwan, to Korea, to fabs around the world. Well, it worked in San Diego, but once the equipment gets assembled and it settles in and gets broken in, and a few days pass, everything is off and it doesn't work anymore. So it was clear that it was a control problem. It was a problem of maintaining the light in the face of uncertainties in the hardware. Cymer tried many things using cameras, trying to model the fluid dynamics, trying to model the droplet blasts, trying to model the gas shocks through which the droplets travel and so on. None of that worked. A student of mine that was hired, Paul Freehoff, the same guy who did his PhD on Nash equilibrium seeking for games. Paul had joined Cymer, and he suggested, well, don't you guys just want to generate light and maximize its intensity? There is a method for maximizing the intensity of whatever you want to produce. Shouldn't be enough to measure the light intensity and adjust the aim with the lenses and mirrors so that you should hit the bullseye at these flying droplets every time. By the way, tens of thousands of droplets per second. That's how rapid this process is. That's how many times you have to get it right. It wasn't easy for Paul to convince everybody that his simple idea would be superior to the complicated ideas, but after the complicated ideas consistently failed, they finally were desperate enough to follow Paul's suggestion, and it worked instantly. The result of that is that this was the final thing to make this extreme ultraviolet light commercially viable, and what was at stake was the acquisition of Cymer by the Dutch company ASML, the world's leading semiconductor manufacturing company. Cymer was acquired in 2013 for just under $4 billion. And now just the equipment in UV light sources is about $10 billion per year. In chips, it must be trillions of dollars. So this is, to my knowledge, the most consequential use of backstepping so far.
Incredible story and incredible impact also on one of the most important, if not the most important industries out there, at least today. I was just looking at how much is the value now of ASML. It's 49 billions as of today in total assets, which is insane. So I hope we've done a little bit of justice to some of the applications of your work. If there's time, maybe we'll cover others. We didn't talk about, for example, before we mentioned extremum seeking and source seeking. That has been, to my knowledge, applied also on NASA's Mars rover Curiosity. As you also mentioned before, the Los Alamos National Laboratory extremum seeking, or if I understand correctly, has been applied to particle accelerators. Let's see whether we have time to talk about that also as well.
By the way, Alberto, I just checked on my phone. ASML is not a $40 billion company. It's a $287 billion company.
Oh, wow.
In case they're listening.
That makes sense, actually. I was looking at Wikipedia now, but it seemed a bit too low from what I understood. Okay, incredibly, we're not done yet. There's way more to talk about, because as we move progressively towards the present, the topics that you studied in your academic journey also touched on some issues that are a bit more in vogue, let's say, these days. One is safety, and the other one has to do with the interaction with machine learning and controls. But I'd like, if you like, to start with safe control and basically your personal interaction with the subject.
This is maybe more interesting from the aspect of what a researcher who once was young and a disruptor in the field might experience when he no longer is of that age. I'm talking now about experiences a couple of years ago. I'm 60 now. So in the late 50s, I find myself that the subject of nonlinear control has moved from stabilization to safety, justifiably because of autonomy, robotics, and so on. Safety is the name of the game. Control barrier functions rather than control the output of functions. What I used to do is so passé all of a sudden. The deepest impression on me was left in 2013 when Aaron Ames presented his first conference paper with Jesse Griswold and Paolo Taboada at maybe an ACC. And I was there in the first row watching this in awe. And with the sense that not only is this important, but it seems I've come across this before, but I can't put a finger on it. The use of the LGV control is reminiscent, the barriers are reminiscent. So it's really incredibly embarrassing that it took me more than a decade to realize what this relates to. So back in 2006, a colleague at Los Alamos who was funding me, and that's important, suggested, Miroslav, do you think it's possible to do non-overshooting control for nonlinear systems? Because in my PhD at Texas A&M, that was my PhD, non-overshooting control for linear systems. And, having so many other things on the plate, I wanted to do it, but with minimum time. So I sat down, worked out the solution It took me 2 days to work it out, type it up quickly, submit it, and this was published in the Transactions on Automatic Control. I was frankly a little embarrassed because I had a sense that compared to stabilization, where one gets completely optimal functions and so on, this result on non-overshooting control was not elegant. It was not elegant because there were some kind of intermediate functions which would later turn out to be barrier functions, but I did not recognize them as such because nobody had even coined that term. It was coined a year later by Frank Algauer and a co-author. There were some conditions that I had to impose to make sure that non-overshooting control happens without any restrictions on initial conditions except for the output. So later on, I finally understood my paper once I saw some other papers. These high-order control barrier functions, which I had used in the backstepping solution for non-overshooting control, were coined 10 years later, a completely independent discovery of this. And then I finally understood why what I was doing was not inelegant. It was not embarrassing. It was completely something unknown to me at that time. So feeling that safety is the subject important at the present time and that I could have something to say on it, I've returned to it. And the one thing that particularly was on my mind and difficult to answer is why are these safety filters, the so-called quadratic programming-based minimum norm safety filters, why are they chosen that way? Why is that the only possible choice? I mean, after a decade in stabilization or 2 decades in stabilization, you know that there are many, many possible choices for feedback if you have a CLF, and therefore there could be many possible choices of safety feedbacks if you have CBFs. Additionally, if the QP, min-norm control, is of the LGV form, there should be a possibility to make them inverse optimal over an infinite time horizon rather than optimal only pointwise in time and in the state space. So I finally sat down and after thinking a lot about how to formulate that problem, which was not obvious up front, I found a way to develop this formulation and find a class, to expand the class of safety filters to those that have the inverse optimality property. And inverse optimality is in the sense that they maximize the safety while at the same time minimizing the deviation between the control applied and the nominal control. So that is sort of my direction in studying safety now that I'm back into that more contemporary subject.
It's amazing. I was looking up also, for context, the original paper that you mentioned by Aaron Ames, Jesse Grizzle, and Paolo Tabuada. There will be a link in the description. We mentioned several keywords. I think it would be nice for the audience to clarify also what they mean. We mentioned, for example, control Lyapunov functions. This is a concept that, to my knowledge, has been developed by Eduardo Sontag, whereby we're adding essentially an input to the concept of Lyapunov function. It's a very important concept in nonlinear control. And as you say, this is very much related to the concept of control barrier function, whereby the input somehow plays a reciprocal role.
Yeah, a control barrier function is such a function that at each point in state space, you can overbound its derivative by the negative of a class K or extended class K function of the barrier itself. But in plain terms, in plain English, a control barrier function is such a function that can be prevented from decaying towards zero, namely from the system reaching and crashing into an obstacle faster than a prescribed time. So you want to allow for it to go to zero, but at a rate that you can control. And there is a very mathematical way of saying this, but we don't have a whiteboard in front of us.
Yeah. So what you mentioned before about inverse optimality is related to a paper that you wrote again as a single author in January, published in January 2024 on the transactions on automatic control, called Inverse Optimal Safety Filters, which I found very fascinating because, as you mentioned, it brings up some very simple examples and then obviously generalizing this concept, showing that if you choose barriers in a different way, then you can actually give a different way with respect to quadratic programs. You can actually interpret the solution in terms of an inverse optimal control problem. So the control law is essentially minimizing a certain cost. And the cost has a very clear interpretation from what I understand.
Yeah. I'm glad you used the word minimizing. I used the word maximizing
I was about to say
safety. No. This is at the heart why I did not instantly understand what I need to do, but it took me years of sort of returning briefly on various occasions and not understanding what I need to do. In comparison to inverse optimal stabilization, where you're minimizing a positive definite metric on the state and on control, you're maximizing the safety, or you're minimizing the unsafety. And this is expressed in words. It sounds so simple, but that was the barrier from seeing it. I just could not envision that as the objective, to minimize the unsafety. And then it came all together once I realized what I need to do.
I'll put a link, obviously, also to the technical note on transactions on automatic control that you also mentioned before, and non-overshooting control of street feedback and nonlinear systems. As I mentioned, the breadth of your work is mind-blowing, so we're kind of galloping through these topics, and we could easily do an episode on each of these. I really wanted to talk about another topic that I found very fascinating when I witnessed your body lecture 2 years ago on the interaction between, let's say, deep learning and control. I don't know how to best introduce the topic, so maybe I'll leave it to you.
Yeah. So my safe control or control barrier function story was prefaced by saying that I had finally, at my age, begun to feel like a dinosaur. And that's not a great feeling if you've been quite the opposite 25 or 30 years ago. And the second experience is related to machine learning. Machine learning began to intrude into my research seriously around 2021. First, a student of mine who spent a few months at Berkeley working on traffic control went there carrying backstepping with her, Juan Yu, and we have a book together that appeared a couple of years ago. Juan went to Berkeley with PD backstepping to work on traffic control and returned with an implementation of reinforcement learning for these PDEs. That was the last thing I wanted to see. That after 1,000 iterations of reinforcement learning, a feedback law is produced, and I don't know if we're talking hours or if we're talking days or minutes, it doesn't matter. We're talking much less than 3 years, which is what it takes perhaps to become an expert like Juan in PD control. That after 1,000 iterations, these reinforcement learning controllers nearly match the performance of the backstepping controllers for that class of PDs. You have to do it offline. You can't do this in real time because you would have crashes hundreds of times before reinforcement learning starts getting good enough. But still, it is striking and from that perspective, depressing. Another thing that again intruded and reminded me what a dinosaur I was becoming was an invitation to give a talk at a very famous, I think, online seminar series, Control Meets Learning, which took place in 2020 and 2021. Everybody there was speaking about some version of a use of machine learning, reinforcement learning, connected with control systems. It was a nightmare for me to decide what to do. To decline or to speak to young researchers on something other than what interests them. I managed to put together something. There was a little bit of reinforcement learning on traffic control, but it became clear to me that if not for my sake, then for the sake of my students who need jobs, who, whether the jobs are in industry or in academia, they need to connect with data-based methods. And at that same time, a new faculty member arrived at UCSD, Yuan Yuanxi, in the electrical engineering department. She had invited me to speak in Control Meets Learning. She was a very talented person, learns at an incredible speed, willing to get into PDEs. And I thought about how these two things can be combined without me walking away from PD control, model-based PD control. Not throwing away that, but building on it and combining the best of both methods. And I found that the way to combine things, the way for a coexistence between advanced model-based control designs, which are our field's heritage, and machine learning methods, is in the implementation of these complicated control designs. And nothing's as complicated as PD control, perhaps. So it was a perfect match, which resulted in 1,000-fold acceleration of the real-time computation needed, namely replacing the solution of PDEs in adaptive control of PDEs implementations by neural operator maps, which are learned offline. And that is what I chose for my body lecture in 2023. I worked on it, I think, continuously for a year to get it right for an audience that is not necessarily in either of these fields and can still follow it. I want to mention a key person in this. It's a PhD student, still a PhD student, Luke Ban, an incredibly talented student who picked up all of these things from PD control to machine learning to computation.
Amazing. I was just trying to find the section of the paper where at some point you say no background in machine learning is needed to read this paper, because I found it particularly funny. And also in the introduction of the paper titled Neural Operators for Bypassing Gain and Control Computations in PDE Backstepping, as you mentioned, written with Luc Ban and Yuan Shi, the introductory sentence I thought was a gem. So machine learning, artificial intelligence, often not entirely unjustifiably thought of as an existential threat to model-based sciences from physics to conventional control theory. That's what you state. And then obviously you carry on showing that actually, well, the gist of the paper, based on what I understand, is that machine learning enables, as you say, the computation of control gains for PDEs in a way that is computationally, obviously this is done offline, but is computationally way, way more efficiently, at least in terms of time. And therefore, it actually provides, it assists control design in the sense of computation, which is, I find, a very nice message to give, a message of hope somehow for control people, in the sense that model-based designs do still have a place in our field. And maybe these tools actually can serve as assistants, computational assistants to our design, which I find, I don't know, particularly a very nice message overall.
Mm-hmm. Thank you. Thank you.
And then I know, okay, thanks to our interaction offline, that you're going back to the roots in these days. So you're writing a new book with Karafillis on adaptive control, and I'll let you introduce the topic.
Well, the time goes on in this podcast, and the time goes on in general, and we're now, there's a predominant theme of what happens in a later phase of a career stage. And one of the things that are nice at a relatively late career stage is that you don't have to justify yourself to anyone. If you want to return to topics from the past, which have long been given up by everyone, and not care if some mistake that action for being a dinosaur, being stuck in the past, I don't care. Recent work that really is worth highlighting is the work with Iason Karafillis, my collaborator on the largest number of papers so far, and a professor of mathematics at the National Technical University of Athens, an incredibly talented person. It's an interesting story in the following sense: how wrong you can be and how doubting people can motivate them. So we're walking through Belgrade, Iason and I, after we had lectured a short course on control systems with delays for that European Union graduate school. And he says, you know what? The thing that I want to work on in the future, and I think it's maybe the most important thing, is adaptive control under disturbances of arbitrary size. And I'm horrified, because to realize that that's a hopeless problem, it takes maybe 5 years. It takes reading so many things and trying yourself new ideas and failing, and it inevitably ends up impossible, even though you can't prove that it's impossible. And I try to express this to him in a way that is not arrogant, but the message is clear. the message was taken as a challenge, as an inspiring challenge for Jas. So a few years later, our interactions with this problem start in earnest, and every idea that he shares with me looks not unpromising. It does not seem to lead to the dead ends that I've seen in so many forms. Fast forward to where we are now, we have results that establish that one can ensure, in the presence of arbitrarily large disturbances, not just a form of input to state stability with respect to those disturbances which was absent before, but one can ensure the convergence of the state to a residual set of an assignable size, namely arbitrarily small size, no matter how large the disturbance is, and no matter how large the parametric uncertainty is, without any knowledge a priori on the parametric uncertainty. For Jason, the mathematician in all of this, the driver was that none of the existing stability theory covers it. It had to be developed from scratch. And it was his desire that this be published more than just occasional papers, and we have recently completed a book which is to appear with SIME by the end of this year. The method, we have named it Dead Zone Adapted Disturbance Suppression. The acronym is DADS. Dead zone is crucial here. This is not based on the sigma modification. You can't do it with a sigma modification. You need to use the dead zone, and you need to fortify the controllers, and that's the ticket to finally achieving robustness of the kind that's always been desired.
Amazing. I love the preface of this book. There's a moment where, well, a sentence where you say, regardless of the challenges encountered, researchers will never stop aspiring to controller improvement in real time using adaptation. I thought that that was a real gem. And the question I had for you in this regard, so I've seen, obviously, we're not able to link to the actual book as of now, but we'll link it in the description after it comes out. I was just curious about this construction of the DADS. So what is essentially, so the results are somewhat mind-blowing in a sense, because it seems to deliver too much, or something that, as you say in the preface, folklore has acknowledged as impossible to achieve. So I was wondering, what is special about the dead zone element in this construction?
So I have spent weeks, at least, if not months, trying to distill these ideas to their simplest form. You know, it's easy for me because most of the creation is Jason's. So by the attempt to trivialize them, I'm not trivializing my own. So I've finally gotten to the point where I can answer this question, which is really the most important question. What is the key idea? What did everybody else miss before? So first of all, the dead zone, as you mentioned, is crucial, but that's not the novelty. The dead zone was present in as early as a 1982 paper by Narendra and Peterson, and has been used a number of other times. The dead zone is crucial in preventing the drift, but it is not the novelty. The novelty is in the controller. The controller uses a particular form of nonlinear damping, which ensures that the effect of the disturbance and of the parameter uncertainty is suppressed. But nonlinear damping is not new either. Nonlinear damping is a nearly trivial concept. It's just a completion of squares in the simplest version. What can possibly be original in the completion of squares? Only in what you apply to. So there is a non-trivial way of handling the effect of the parametric uncertainty and the effect of the disturbance, which results in a form of nonlinear damping where you don't apply nonlinear damping with a constant gain, as in all the previous work in robust nonlinear control and robust adaptive nonlinear control, but a form of nonlinear damping where the gain of nonlinear damping is being updated, being adapted, and subject to the dead zone. And it boils down to the several steps of completions of squares, but not of the kind, not used before. Several very specially sequenced trivial operations, and that's the essence of it. Everything else is a generalization, which is far from a routine, but the essence is what I attempted to describe.
Fantastic. I mean, highly recommended to our audience. I'll quote also what you cite in the end of the preface from Winston Churchill. You say, now this is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. We'll see. Time will tell. But I think this will be something that will be recognized as very important in the future.
The credit for that quote goes to Jason.
I particularly enjoyed it. So I'm also mindful of time. I think it would be nice to gradually shift towards the end of the episode. There is a set of questions that I normally ask every guest. I thought, given your special role as also the editor-in-chief of Systems and Control Letter, we could talk about several aspects, if you want, of research. For example, the research service tension. We also mentioned briefly the theory versus industry tension and the role that editorship also has in research. I don't know what you would like to talk about.
Well, let me try to address all of it through a common denominator. All of these things are something other than research. Being editorship, being service to the society, be it service to your own university, or be it working with industry, which won't necessarily translate into academic publications in premier theoretical journals. I have found it really, really important to be pulled in some other direction and not obsess over just an endless stream of technical details and possibilities that could be explored. Only after you're forced to do that, you realize the benefits. And the benefits are that co-authors, primarily the students, take more control of things. You relinquish control, they assume it, they leave more of an imprint over that, they develop their own voice, and that's beneficial when you're forced by editorial work, service work, to treat research as one of the components. Regarding the work with industry, I was thrown into that in an interesting way. I had an offer from another institution. It was an excellent offer. UCSD wanted to keep me. The other institution wanted me to start a center there. My dean said, you can start a center here also. But I want you to start it the way I envision a center. It can't be just theory. You know, there's an opportunity to engage industry. You start bringing in companies. I say, Frieder, have you looked at my papers? I mean, companies, yeah, I've done a little bit of that, but to turn this into a deliberate model, I'll try, okay? So that is how the systems and dynamics at UCSD started, with the support from Cymer and General Atomics, and various other industrial collaborations were flowing into that with United Technologies, Ford, Los Alamos, and so on. And it benefited our students. The students connected with great jobs. I think the relevance of our work advanced, and so on. This is what also led into my administrative appointment. It didn't take a lot when an opening for an associate vice chancellor for research was available for somebody to think of me as somebody who could be overseeing institutes and centers at UCSD. And I am now entering the 14th year of that service. At the beginning, it was a lot of work and management. Now it's more like mentorship, more like reliance on experience rather than labor. The editorial work is one of the more interesting, more rewarding, most rewarding, and most complex things. No offense to anybody serving our society in all the important roles, but the intellectual reward of giving feedback on the actual research, and sometimes having to give feedback that is rather negative, but takes the authors in a direction that will ultimately advance the relevance of what they're doing, or make them aware of all the other things that others have done that they haven't come across because they have looked only narrowly and over a limited time span. I find that incredibly rewarding. It's even when I end up projecting without review 6 out of 10 papers in a week, and a lot of it is just consuming my time and I'm learning little, knowing that they are learning something that feels like a worthy mission. Also, the associate editors, the senior editors, everybody's advancing in some way, and we are expanding the pool of people who are doing valuable and fair service to others and feeling recognized for that. But at least, one person who is working closely with them on that, that's also rewarding.
Fantastic. I think you anticipated the question that I would have had for you. That would be, what motivated you to get into editorship? And I think you expressed it very clearly. I have one more question that I normally ask. Well, I do ask a few to every guest that comes on the show. One is that of advice to future generations. So things that you would have liked to know when you had started your own career, or topics that you may deem important for the future of the field. And maybe a curiosity of myself that is more related to who the academic heroes that you might have.
What would I have wished to know when I was starting out? When I was finishing my PhD, I had produced plenty of papers and felt ready to operate independently and had a lot on my to-do list. And doing a postdoc seemed completely incompatible with those desires and mission. In retrospect, having done a postdoc would have been a wonderful thing, expanding the experience and connecting more broadly, socially, enriching myself academically. Regarding what I see as a future of the field, or what I might recommend to people entering the field, I'm always reminded of a comment that Larry Ho, retired from Harvard, made in one such situation where he was asked to do that. And he put it very bluntly. The only thing you're ever going to get as an answer to this question is what the people answering would like to do over the next year or 2 years or 6 months. And that is how I feel. That question is incredibly difficult for me. I maybe know what I'd like to do over the next few months, and it'll probably change, and that's a good thing. That's in the nature of research, that we'll find some better idea along the way. As far as making some recommendations regarding style to young researchers, I manifestly would want to stay away from any. I think there are as many approaches as people. Everybody has to find their own voice. I think my experience, to be generalized, would be a terrible recommendation to a lot of people. So maybe an occasional steering away from mistakes is valuable, but being prescriptive, I don't think so. So finally, about heroes. I don't have time to speak at length about Peter Kokorovich. That really is merited, but there is not time for that. People who know him know what an amazing intellect he is, how wise he is as a mentor. So regarding myself, the experience was definitely that Peter got out of me what I didn't even know I possessed. And after that, I just couldn't stop. And another feature of Peter is that he doesn't hesitate to be critical. And he understands instinctively that if the criticism is understated, it might be mistaken as optional. So his feedback, often people who have worked closely with him, is really tough. And due to that nature, I've been in many ways conditioned to anticipate that I might make a mistake in some occasions. We're not talking about technical things. We're talking, if anything, about matters of taste in all forms of it. So because of that experience, not only do I not feel the guilt when I sometimes go pretty strongly with my feedback to my students, not only do I not feel guilty, but I feel compelled to calibrate and give sufficient intensity to that feedback so it's we don't iterate, so that it's assimilated and we move on to the next round of situations where more can be learned. I don't know if the word heroes is what I want to use for many other people that I respect and love and consider friends. Regarding, for example, Eduardo Sontag, my career has been at least partly defined by using input to state stability and his numerous other ideas. Jean-Michel Coron is a person to whom I've been looking up to in PD control. These two are mathematicians. Among engineers, I've always been in awe that somebody is capable, like Tamer Bashar, to be at the top of a research field and a pioneer of such a magnitude and lend so much service to the community. Manfred Morari, also want to mention, your most recent interviewee, is a role model for combining research and industry. A person of an amazing record and taste to evaluate yourself against if you're trying to do research with relevance. And in the Department of Mechanical Engineering, I must mention at least one person from that world, the incredible Masayoshi Tomizuka at UC Berkeley, for his incredible impact in industry and as an educator.
Amazing. Well, Miroslav, it's been an honor and a real pleasure to have you on the show. I think we will treasure everything that you just listed, so don't neglect the possibility of doing a postdoc for your own personal enrichment, and don't underestimate, on both sides, I would say, the role of mentorship in your academic interactions. Well, as I said, it's been a real pleasure and honor. Thank you so much for joining us.
Thank you so much for having me, Alberto, and thank you for creating all of this, both for the present and for posterity, and for investing all the time to study and feature the actual science.
Thank you.
Thank you.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.